So in this video I'll be showing these examples. I already did exponential decay for radioactivity and the coronavirus for exponential growth previously, and then I'm going to look at these are barometric pressure, dampening of a spring, national data loads on structured deer, and then several coronavirus cases around the world. Alright, so next section. But this is going to be really interesting because I recorded the following a couple hours ago for 9 minutes and then noticed that I virtually got nothing, and then this recording software just went away. So I'm starting here a little frustrated. Let's see. 2 hours ago it took me 9 minutes. Let's see how long it will take me now. Okay, so 4.6 exponential, logistic, and logarithmic models. And what we're going to look at here is these. So we have an exponential growth and an exponential decay. It doesn't have to be decay necessarily like as in radioactive decay, but an exponential going down. And the difference is that this A here, the base here, is larger than 1, and you get the one on the left. And over here for the other one is that the base A is between 0 and 1. Of course, it cannot be below 0 itself, because then it's not going to work usually with the exponent. So if you think about this one here being A being smaller than 1, for example 1/4, you could invert that, so you have 4 over 1, but when you do that you introduce a negative in the exponent, so -1, so you would have here a negative x, which is kind of what they're saying here, that exponential growth e to the kx, where you have k being positive, and here you have exponential decay e to the kx, same thing, but k is negative. So that's exactly what I just said. All right, let's look at some examples. So here I'm going to have modeling radioactive decay, which I did in section 4.2. So I'm not going to do it again here. Instead, I'm going to choose something else. And I chose a pressure versus altitude relationship. And there are all kinds of things here. I know it says temperature, it says temperature right here, and then here it says the altitude, and then here it says atmospheric pressure, and I'm really only going to use 2 columns here, the altitude in meters and the atmospheric pressure over here. So for example, at 0 meters altitude right here, there is 101 kilopascals of pressure. At 1,000 meters up, there is 89 kilopascal of pressure. At 3,000, there is 69 kilopascal. And I'm not going to graph, obviously, everything. I'm only going to graph a few. So let's look at the data in Desmos. So here you can see I plugged them in. I'm going to put them here, click that little plus button so we can see them actually in the graph. And then I still have to zoom out so they actually fit into the recording. There we can see them. These are numbers I just read off to you, right? 0, 101 kilopascals, 89 kilopascals, 69, and so on. And the higher we go up in altitude, the less pressure goes. And when we graph them, we can see that here is a curve, obviously. Let's see if it's exponential. I've also prepared that. So the variable y phi is proportional to a parameter a in the front, e to the negative, because it goes down, it's a decay. The pressure doesn't decay, it just goes down exponentially. And then here is the variable x5, that would be the altitude plus some b here, not exactly a y-intercept. And we can see that the fit is virtually perfectly, except maybe for this one here. And the reason is perhaps that in this table that you saw a minute ago, those were probably modeled after a mathematical model, and they possibly gave us perfect data, and by me rounding, that's why I'm a little bit off here. Notice the regression coefficient is really, really high. And here a very small parameter constant in the exponent. The reason why it's so small is because we're dealing with thousands of meters, so therefore this one is really tiny actually. But in any case, it's nice exponential decay. All right, where does this actually come from, or why does it look this way? So I pulled up here these here, Earth and its atmosphere, and you have to picture that, well, you have the Earth and you have your really thin atmosphere. No matter what picture you look at, you always will see that. Well, when you go to the layers of the atmosphere, let's see, actually there's a button here, let's see what happens. Layers of the atmosphere, okay, that's not exactly what I had in mind, but it looks pretty cool. What I had in mind is actually these here, that when you look at the layers, the upper atmosphere is pressing down. So as it presses down and down, you have more pushing down here on the molecules, and therefore you have a higher density down here, less density, and the pressure is related to density. So you have high pressure down here, less pressure, and yet less pressure. And all these other here, all these other diagrams, they kind of look similar, and I still pulled them up because they do look kind of interesting. So here we have, for example, comparing to Mount Everest, and they show the same thing: high density here, lower density here, high density here. Why does Earth actually have an atmosphere, or how does it keep it? I'm going to go back to, let's see, these images here. Well, gravity actually pulls it in. So gravity is holding onto the atmosphere, so it's not going to evaporate into space. I'm going to have a couple more pictures of these layering here. So again, high density down here and lower density here, and the same thing for the pressure. And here, one last one. This here it looks like a children's thing with the stick figure, but that's fine. You know, it really shows it nicely that the upper atmosphere is pushed down, therefore higher density and higher pressure towards the bottom, and it exponentially goes down as the altitude goes up. So here's that one again here for the altitude and pressure data, and again here's that equation here, the exponential decay. So I'm going to take these actually off because I want to do another example here. So this is damping of the spring, already recorded data here, and let me show you that. This is from a free software that is available on the internet called PHET, which stands for Physics Educational Technologies. And I'm going to just start a spring here. So there's a weight on the spring here, and it's obviously vibrating up and down, and it's doing exactly what we expect it to do, which is it just swings, vibrates on and on and on, except, interestingly, it never seems to stop. In fact, the way I have it set is it never stops. But of course, there is the air that is going to slow it down. It's called damping. And so let me show you that when I turn it on. I'm going to stop this here for just a moment. I'm going to turn on the damping just a little bit. I think it's off the screen, the button, so you won't be able to see it. But here's what, when the damping is on, and you can see that it indeed slows down. That makes sense as well. Eventually, the air will have it slowed down. So these are the data that I recorded, and I'm going to put this on slow here. So instead of going really fast, it's going to go slow. Notice down here, the bottom of it starts at 100 centimeters. So then as it goes up, it's going to come back down again. I'm going to look here. It's going to be about here where it's going to stop. And you can look at the ruler and see it stops at 86. There you go. Goes up and comes back down, and it's kind of going to be here. That's because I did it before. I kind of know where it ends up, and it's right there, 76. And notice it went down by 14 and then by 10. Let's see where it ends up now, right there at 69. So it is not linearly going down, but gradually going down. And that, of course, would be the exponential. And now we're at 64 here, or I believe there was. So I'm going to go over to Desmos. And let's see, here it is. And that's kind of what I just showed you, 100, 86, 76, 69. I guess it was 63 instead of 64. I'm going to turn these on. I'm going to hit that little plus button again so we can actually see them, get them better on the screen. And yes, it looks like exponential decay. And of course, I put the equation in already. So I'm going to turn that one on. And you can see this one here, nice data. Of course, the data are actually perfect. That is because the software is, even though I did take measurements, that's why they're tiny bit off, because my measurements and they're rounded as well are a little bit off. So, and then it evaluates this one here. You see the negative for the exponential decay, and then this is the one in the front. Here's the parameter 49, and this is the decay constant 0.33. And here's another example for exponential decay. All right, let's go ahead. So here's example 2, modeling population growth. This is about, I'm not going to do this one, but we're just going to look at it briefly. So here is the population of the United States, and it's supposed to rise exponentially from 282 million in the year 2000 to 335 million in the year 2020, which we're in right now. And true, I just looked it up earlier today, it is around 330 million indeed. Not too hard to guess though, because the book was published in 2016, so the latest data they could have gotten from 2015, and so projecting that from then is not hard to do. I will do exponential growth here, but just in fact in the very next one. All right, so growth of the national debt. So here we have a few numbers. I'm going to go over to Desmos, and let's see, that was the last one I did. Take this one off from the graphing and put the national debt on here, and there it is. So here are the numbers. These are numbers you find in a book. Graph them, again that little plus sign here, and there they are. I'm going to zoom a little out so we can see it. Okay, this one is interesting because when we put a straight line on it, it's like, a little bit of a scatter plot, right? But I mean, it's not really that bad. So let's actually put an exponential on there. So again, a times e to the k, and then what is it, x2, and then I put a plus b here at the end. There we go, and yeah, it looks a little bit better, right? And then it would grow exponentially over the years. Down here you actually see the years, 50, 60, 80 years after, like 1975. So here we'd be looking at, roughly here at 130 years, we'd be looking at the year 2100 actually, and it's way, way up there. But that depends, of course, on policy. So possibly it's not going to go up that steep exponentially, and then somebody is going to save a lot of money, some president, some administration, and it's Congress, it's going to flatten out more. We're going to go back to exponentials when I look at the coronavirus. Again, I wanted to click on here. All right, example 4, modeling loads in a structure. So I have that too, because this one is natural log. Oh, I forgot something. I meant to answer a few questions here. So let's see, make a scatter plot from what was estimated natural depth in the year 2010, and you plug in numbers, you calculate, and then you come up with these $15 trillion. Okay, now I'm going to do modeling loads in a structure. And these are data I put in Desmos. So let's look at them. There we go. Oh, I have to hide the other data. And these are data from the book. I rounded them because they don't have to be that accurate in order to plot. And we can see, yeah, they certainly are not exponential. There's something else. Well, that's logarithm. We could put this one on here. Well, it's a little bit of scatter there, but we can also put a logarithm there. So let's see. Times, that was my phone apparently ringing, and then x3, and then I'm going to put a, let's see, is that the one I'm supposed to use? Yes, I'm going to put a plus b on there, and we see that, yeah, that's actually looks pretty good. We also see that these parameters fit the ones that you find in the book. By the way, I forgot to also mention, I don't know, last one on national debt, that the parameters that you saw here on the last one also fit the ones in the book. You know, the 0.033, I think you see. Oh, they did a little different. Anyway, so yes, the parameters fit in here, and apparently that's what this load is doing, so it's not as bad as you put more load onto something. All right. And then we're going to come to the next one. So here we have the logistic model. Now, the exponential, which kind of goes up like this, and the logarithm, its inverse function, goes up like this. The logistic function is actually really interesting. It goes up exponentially first, and then it peters out at a certain, what could be called a carrying capacity when it's about wildlife, which is actually what I'm going to do. This is the way it looks like. It has an exponential, apparently the denominator with a 1 in front, so interesting things are going to happen with this particular one. I'm not going to do the example here. Instead, I'm going to go to, let's see, number 27, which is about white-tailed deer. So this is the function here. I interpreted the problem a little bit different, so what I did in Desmos is actually I supplied a few data. So here it says, it asks how many deer were initially introduced in the refuge. We're going to look at that. How many deer will be in the wildlife refuge 10 months after introduction? So I actually supply some data here. So here they are. Oh, I have to turn this one off. And there we go. So here are data for the deer. Again, I'm going to click on the little plus sign. There we go. Zoom out maybe just a little bit. So here they are, but what I did now is I supplied data after actually 20 months, 40 months, up to 100 months, which is actually 8 years. How did I get these data? Well, I got these data by using this equation here, which is the one already in the book. So that's the way it looks like. There it is. Looks kind of pretty, right? And that's how I got the data. That's why the data are perfect. Now, what I could do with these data is actually put a straight line through it. That doesn't look too bad either. Maybe they're just increasing linearly. Maybe they slow down. For that, actually, I would need more data. But they're saying, hey, it's a logistic model. Apparently, the wildlife refuge has a certain carrying capacity, so let's just assume that. Of course, if I typed in the original one, well, I come up with that exactly the same one here and with the same parameters. So let's look at the questions. So I'm going to plot the graph again. So it says, how many deer were initially introduced into the refuge? Well, that's the y-intercept over here. So apparently 10, no, it's not 10, it's 20 deer right here, 20. We can see that. Now, when you look at this one here at the equation, you can also see that. You divide 300 by the denominator. Well, at time 0, x means is time in this case. E to the 0 is 1, times 14 is 14, plus 1 is 15, divide into 300. That's the 20 that we see here. That's the number that was introduced. Okay, after 10 months, well, we can look at the graph here. It's here, that's close enough to 10 to 9.8 here. So we have either 31 or 32 deer after 10 months. Okay, now what does this one mean as it peters out up here? This one up here is what's called the carrying capacity. So that means that apparently the wildlife refuge has only so much vegetation for the white-tailed deer, or it's only a certain size, or there are enough predators that there can only be a certain number of deer after a while. And here 150 months, that's in the neighborhood of 12 years or so. Apparently that would be 300 deer. Well, when we look at the equation, that's apparently the numerator. Well, how does that happen? Well, for large times, relatively large times, so in this case 150 months, for example, e to the negative here to 150 times 0.05 becomes pretty small. Multiply a pretty small number by 14 is still pretty small. Pretty small, being close to 0, added to 1 is 1. 300 divided by 1 is still 300, and there's the carrying capacity. I will also look at that logistic model when I get to the coronavirus. Okay, I'm going to start with Italy. Today is March 27th, and the recording for Italy I made 10 days ago, I believe. And back then, these are the data I had, a little over 30,000, and the exponential predicted that it's going to go over 80,000 within, well, there it goes, right, within just a few days. As apparently is day 56, so that looks like day 62. So 6 days later, it would actually catch up to China, because China kind of kept steady at 80,000. And there might be a couple of reasons for that. So when I look at the actual data, this is a website here called Worldometer. There you go. I think they have all kinds of statistics, but in this case, they really focus on the coronavirus. So when I scroll down here for the ones, there we go, there's a table. Italy indeed has overtaken China. And so, unfortunately, that's what the exponentials do. They're really steep. When I click on Italy, I can look at the graph and notice that this one here is the exponential. It's a different scale than what I had. So this one, mine is dramatically more, drawn out vertically. This one is a little squeezed. But there might be something going on here just in the last few days. Notice that this here is exponential. It ought to go on like this. But in the last few days, it looks almost linear, as if there's like a straight line. Linear is better than exponential. And the best, well, we're going to see that in a moment when I look at the logistic. So let's go back and let's look at China. And China looks like this here. So it was exponential at first, and there was another big jump. I still don't understand what happened here on February 12th. And then it actually petered out. So there's the logistic one. Now, this here looks almost too perfect. Really, they just have a few cases every day. I'm not so sure about that. It is definitely a logistic curve, and I'm going to go here in Desmos. I'm going to look at that. So I'm going to turn off Italy. And let's see, here it says, in my Desmos, it says that Z1 is China, published data, adjusted data. I'm going to do both here. So let's see, Z1, U1, I believe. So what I did here is, when I turn this one off, you can definitely see it's, yeah, it is a logistic curve. There's this big jump on February 12th. Let's assume that I turn it off, that there was something really strange going on with the reporting. I get this one, looks better. And then let's see, my logistic model, where did I put that? Here. And you can see, wow, that's really right on there with the carrying capacity apparently at 67,000. So it's a, well, that again, that's the 12,000, the extra 10,000 or so from February 12th. Let me go back to the other data, the unadjusted one. The data they actually reported. There you go. There's the 80,000, right? And we can see, yeah, it does fit the logistic one quite well. Again, I don't know where that jump came from. And so, yeah, it fits this particular logistic curve. And when you look at the carrying capacity here, I mean, the top infection rate, 80,000. Let's look at Korea, that is South Korea. All right. And there's an interesting development as far as the curve is concerned. So here you go. You definitely see the logistic model, but it definitely goes up like that. So what I did 10 days ago is I was just at the beginning of that. So let me see. U4 South Korea is what I'm saying. So I'm going to turn this one off. I'm going to turn China off and get to South Korea. U4 is what I chose. I have to go up and down here to actually find it. There it is. Hit the little plus sign. There you go. And it's actually kind of continues like this, linear. It's not too steep there. So, and here's the regression curve here. So here it says it ought to peter out here. This would be the true logistic, but you saw that from the worldometer right here. It actually continues on a straight line. Again, the scales are not exactly the same, but I think in my curve you can see this bump and this bump here and this bump down here. Let's see if that's true. Where'd it go? Where did it go? Oh yeah, there. Yeah, maybe here, right there and right there and right there. So this one still is going up a little bit, and the scale is totally different from China. You know, China has 80,000, so does Italy, and South Korea apparently has not even 10,000. So they really seem to have it contained. And I think these data are more realistic than the China ones, because this one here still shows it going up. It's still ought to go up. I mean, totally flat as if it's eradicated. Oh, I don't know about that. That's wishful thinking. But at least they seem to really have it contained. And among the many countries, that's virtually the only one that I've seen that. All the others are still quite exponential. So again, the logarithmic model actually fits this one here quite well, and the same thing for China, even though I'm not so sure about the latest data. So let's look at a few really exponential ones. Oops, that's not what I meant to do. I'm going to turn South Korea off here, and let's see. Oh yeah, I wanted to go here actually to the worldometer website. Go here, for example, Germany, 50,000 total, and we can still, the exponential, yeah, here it slowed down, but then the exponential took over again. So I was hopeful here just a few days ago that it becomes linear, but then it actually started to increase again. France kind of looks similar to that. Here we go. And then here, it's steep linear. Maybe it's still exponential, hard to tell. Here, I was hopeful right here, but, you know, things happen. So let's look at the data for the United States. Notice the United States is now, this is March 27th, as the most infections with 100,000. And so here, oh yeah, here are all the states, including Alaska down here is at 85. And then here we go. Here's still an exponential. Definitely. Let's look at the Desmos for this one. I didn't plot all the data. I plotted every third day, but that's sufficient in order to actually see something there. So I just have to find that. By the way, today, March 27th, is my last day in my office at the college because the governor said we have to be all at home, no exceptions. So here's the data for the United States. There they are. Again, show it up here. And then here is the regression model, which is an exponential. And you can see it adheres quite well to the exponential, unfortunately. So hopefully something is happening to keep this from happening, just going straight up and straight up there. So I posted, or I didn't post, but I made a couple of questions here. So let's see. What do I say here? So the model shows this. Let's see if that's true. 0.26 and 0.0043. Yep, there it is, 0.0043 and 0.26. The B here is really not that important there. That's just to adjust a little bit. And then I'm saying, okay, I based these data on February 15th through March 25th, every third day. So these days 25 through 64, day 25 being February 15th, kind of like after January 20 when it really started. Okay, and I posted a few. Again, I didn't post these questions here. I just show them to you right here. Why is the factor A 0.0043 so small? This one right here. Oh, I'm sorry. This one right here. So why is it so small? Well, that's because the first data point was the 25th day of the worldwide pandemic, and in the first 20 days, the United States had virtually nothing, so that factor is very small. And then here is a statement that I actually didn't finish. I don't remember what I wanted to say there, but what's really important, yeah, is that it is exponential. That's probably what I wanted to say. There we go. Okay. When will there be 1 million people infected? Well, to set that up, I take this equation here, the model, the exponential model, and I set it equal to 1 million, and then I can solve for time. So that's what I did here. So 1 million is this one here. Why did I cross out the minus 290? Because when I add the 290 to the other side, it's still 1 million. So I really don't need it. So I solve for time, which means I'm going to divide. I'm going to put the calculator here. So I'm going to divide 1 million, 1 times 10 to the 6th. This E here is not our E. This means that's an engineering E, meaning the number of zeros afterwards or decimals. So 1 times 10 to the 6th is what that means. Divide by the factor in the front, so 0.0043. Come up with a really big number. Now I have to look for the t in here. So I have to get rid of the e to the something. Well, the way to do that is take the natural log on both sides. So I'm going to do that. Natural log of the answer that I just had. I come up with this one here, 19.26. And last thing to do is that equals 0.26 times time. So I divide that one by 0.26. And I come up with 74. What does 74 mean? Well, that's the 74th day after the virus started. So 74 days after January 20th, or 9 days after my 10 days after my last data point, which is March 25th. So that puts us to April 4th. If this continues, today is March 27th, if this continues, we will have 1 million people infected in the United States alone by April 4th. That's what exponential means. All right, so other question here. When will all 330 million US Americans, remember that other question earlier, so I looked it up, infected if it continues to grow exponentially? So therefore, do something similar here. So solve, I'm going to see, put on one line here. So solve this one here for time. So actually, I'm going to write this one here, time equals 74. I just did that, didn't I? So 74 here. And then, as I said, 10 days on top of day 64, so from March 25th, that puts us to April 4. Well, check the news if that's actually true. Okay, so now, when we'll all be infected, if this goes exponentially, continuous. So again, if I add the 290 to 330 million, that really doesn't matter. So I'm going to type in these others. So actually what I'm going to do is I'm going to go 3 steps back. Oops, that's what I meant to do. And here we go. And basically, because it's the same calculation, so instead of a 1, I'm going to have a 330 times 10 to the 6. That's what that means. Divide by that small number, gives me a large one. And of that, again, I have to take the natural log because to get rid of the e here. So I take the natural log of that number. There we go. I come up with 25. That 25, again, is being divided by 0.26. And I come up with 96 days. What does that mean? Well, 96 days is 32 days after my last data point. 32 days after March 25th is April 26th. Again, another scary date that within a month every US American is infected. If we're not able to contain that. And this is what exponential actually means. All right, here are the data for Alaska. Actually, I have to turn the other one off. Alaska, of course, has very small numbers, but of course it's still, compared to everyone else here, the others were countries. You know, this is a state, a low population state. So I think I went to maybe a couple of days ago. Oh yeah, I meant to click that little plus sign there. There we go. And let's see. And hard to tell what we can see so far. You know, here's in the exponential curve. Is it really exponential? I mean, the governor just ordered a hunker down issue for the entire state for everyone. So in order to contain it, here's a linear model. You know, is it maybe linear? We just don't know yet. I mean, we're hoping it's linear and then become logistic and kind of tops out. So let's see how that is going to work, hopefully.